Okay, today in class we're doing a bunch of problems about rotating and volumes, so integrals and limits of integration and radiuses. Okay, so it's really important for you to determine what the radius or radii are for your picture, okay, and which axis you are rotating around. Okay, so here is, of course, example 1. We have the lines y equals 4, x equals 6, the y-axis and the x-axis, and we're rotating it around the x-axis. Okay, so here we have the line y equals 4, right? It's a horizontal line 4 units up. And we have the line y equals 6, which is over here. Okay, so we have this nice area that is a rectangle. Okay, and we're rotating it around the x-axis, which is this axis right here. So here is your axis of rotation. The line y equals 0 is the equation for your axis of rotation. Okay, and when we do this, when we rotate a rectangle around a central axis, we're going to get a cylinder as the shape. Okay, so we're going to get a cylinder. Okay, so in geometry, we would have found the radius for this cylinder and the height for this cylinder. Okay, but this is not geometry, this is calculus, so we're going to use calculus. So the volume is pi times radius squared, because the cross-section of each of these, I guess, rectangles that you rotate is a circle. Okay, and a circle has, of course, pi r squared as its equation. Okay, so we have, since it's an x-axis rotation, we need to have an x equation, and we need to have x limits of integration. So first of all, if we're looking at the limits of integration, this is basically the height for your cylinder. Okay, so the limits of integration are from 0 to 6. Okay, so your limits of integration are the height for your cylinder, so from 0 to 6. And then the radius is, of course, the distance from the farther equation to your axis of rotation. So in other words, 4 minus 0. Okay, because this is the line y equals 4, and here is your axis of rotation, y equals 0. Okay, now it's pretty basic for this one, but as we continue with these problems, it will become less basic. Okay, but the problems, the idea is still the same. So the volume of this cylinder is pi times the integral from 0 to 6 of 4 squared. And of course, 4 squared is 16 dx. Okay, so if you have a calculator, it's handy to slap that in there. If not, then of course we take the antiderivative of 16, which is 16x, evaluate that from 0 to 6, okay, which means 6 times 16 is 96. 96 pi will be the volume for that cylinder. Okay, when we rotate that area around your x-axis, we get a total volume of 96 pi. Okay, so that one was pretty easy. Let's look at some others. Okay, look at this one. Here we have an equation that says y equals x squared, the y-axis, and the line y equals 4. So let's make a little sketch. Here we have y equals x squared. It starts at the origin. If we go 1 to the right, we square it, and that's 1. If we go 2 to the right and square it, that's 4. So here we have the graph of y equals x squared. Okay, it graphs to a parabola. And here is the line y equals 4. Okay, so this is the region that we are rotating between the line y equals 4 and y equals x squared. Okay, so we're rotating it around the x-axis. Okay, this is your axis of rotation. Y equals 0. So if we were to think about this, think really hard about this, right? We would have a reflection that would be down here in the bottom quadrant, and it would look something like this, right? Where we have the cylinder, so we would have a cylinder shape that is missing this funnel on the inside, right? So be a cylinder minus this funnel would be the shape of your three-dimensional solid, okay? The shape's not that important, but the calculus is. Okay, the calculus is. So every time we rotate something, we have the equation volume equals pi times r squared. Okay, so once again, we want to think about the heights. The height of this cylinder is right here. So those are your limits of integration, so from 0 to 2. Okay, we're doing an x-axis rotation, so we have x intervals as your limits of integration. Okay, x-axis rotation as x intervals. So now let's think about the radiuses, right? There's a couple different radii involved here. So the first radius goes from the top to there, yes? So the first radius is 4 minus 0 squared, right? 4 is the farthest thing from this axis of rotation. So that's your first radius, R1, minus your second radius. Okay, your second radius is formed by our graph, the difference between the graph and that also. Okay, so the second radius happens from the difference between x squared and 0. Right? And since it's radius squared, we have to square this term, and that's going to be your dx. Okay, so no, we don't have to write the 0 in there. Of course, mathematically speaking, that isn't important, but it is important to our understanding of how we do the problem. It's the farther function minus your axis of rotation minus the closer function minus its axis of rotation. So it's the volume of your outer cylinder minus the volume of your, I guess, the non-shaded region here also. Okay, so this can be simplified a little bit before you plug it into your calculator, or you do your antiderivative of 16 minus x to the 4th dx. Okay, when you square x squared, you get x to the 4th. When you square 4, you get that. So to antiderive, we have 16x minus x to the 5th over 5, and we're evaluating this from 2 to 0. Okay, so of course you plug in a 2, you get 32 minus, I believe, 32 fifths, right? You combine like terms, you do all your other wonderful math, and we should get an answer of 128 pi over 5 cubic units as the volume of this cylinder minus funnel. Okay, so the idea is you have to take your farther function and subtract your axis of rotation. Okay, pretty okay when it's 0. But let's look at an instance when it's not 0. Okay, so looking at this guy, we have the region bounded by the line y equals 4, x equals 6, the y-axis, and the x-axis. Okay, so that should be pretty easy for us to sketch. Once again, it is a rectangle. So we have y equals 4 and x equals 6. The x-axis and the y-axis. So this is our rectangular region, same region as we started with in the first problem. Okay, but now we're going to rotate it around the line y equals -2. Okay, so we go 2 down, and now we have the line y equals -2 as your axis of rotation. Okay, so if you want to think about rotating this one, okay, we're going to end up with that same cylinder, right? We're going to have a rectangle down here. It's 2 units above, so it's 2 units below. Okay, so we're going to have a cylinder from the outside, right? A cylindrical figure when we rotate a rectangle with a cylinder missing from the inside, right? So this is like a roll of toilet paper. Okay, so we're going to have to do some type of a subtraction, right? But the calculus has the same idea. So remember, we're still rotating circles, so pi times the integral from, okay, we still need the height of your rectangle or the height of your cylinder, which is from 0 to 6 still, right? So your x intervals are from 0 to 6. But now let's look at our radiuses, your radius. So the first radius goes from your red line to the axis of rotation. Okay, what's the equation of your red line? I believe that was y equals 4 minus the axis of rotation is -2, right? So now it's not 0, it's something else, squared. Okay, so that's your first radius, the outer function, minus your axis of rotation. So 4 minus -2. 4 is the line right here, right? This is the function. Because it's a horizontal line, it doesn't have an x, but it could be a curve, yes. The higher, the farther one. And then we have this radius, right? This is our second radius from 0, the x-axis, to also -2. So minus 0 minus, once again, -2. Okay, and of course, you don't actually have to write this out. Hopefully it's fairly obvious to you, okay, that your first radius is 6 units. Okay, that's your first radius from the red line to the green line, minus the second radius, which is the blue line to the green line, right? So we have these two ideas that you're subtracting your function minus the axis of rotation. Okay, minus the axis of rotation. So this can clearly be simplified. I think we can all tell. 6 squared is 36 minus 4 is basically 32 dx. Okay, so the antiderivative of 32 is just 32x evaluated from 6 to 0. Okay, when you multiply 6 times 32, we get 192 pi cubic units. Okay, so if you're not using an axis as your rotation, you have to take that into consideration when you're finding the length of your radius, right? The radius is from your function to your axis of rotation. Okay, that's your radius. And we have the outer radius squared minus the inner radius squared. We're combining two of them. Okay, well that's all well and good. What if we rotate it around the y-axis? How does that change your function? Well, let's find an example when we do that. Okay, so let's look at this one. We have y equals x squared. We have x equals 2, and we're rotating it around the line x equals 2. So let's see if we can wrap our brains around what this shape is. So we have your quadratic, okay, which goes 1 over 1 up and 2 over 4 up. So you have your quadratic curve. And we have the line x equals 2, which is this. Okay, so this is the area that we are rotating. Okay, we're rotating this area right here. Okay, which is a curved area because of our x squared graph. Okay, and we're rotating it around the line y or x equals 2. Okay, x equals 2. So the graph is going to end up over here, right? We're going to get some type of a semi-conical, semi-volcano looking thing, right? It's going to be curved at the bottom, maybe like a bell or the horn of a trumpet or something like that, right? If you want to think about what the shape looks like, okay, which is nice to think about, but mathematically speaking, right, that might not help us very much. Okay, so we have this horn-looking thing that is we're trying to find the volume of. Okay, we're going to rotate it. Now we have done a horizontal rotation. horizontal rotation. So all of our functions need to be y functions. Okay, when we do a vertical rotation, we're looking at x's. Here, we are looking at y's. Okay, so our volume formula doesn't change because we're still getting circles. Pi times the interval from, well, since we have a vertical or a horizontal rotation, we need to have vertical intervals, right? How much are we rotating? We're rotating right, this is now the height for your, whatever it happens to be. So it's from 0 to 4 is your y interval of integration. Okay, so we need to figure out what the radius is. Okay, how do we find the radius of this function? Okay, so, right, it's a horizontal radius, so we're finding the difference between this curve and our line. Okay, so if we had y equals x squared, that means x equals the square root of y, right? Because this is now an x distance. Each one of these points represents the square root of y for some value of x. So your radius here is whatever the square root of y happens to be minus 2. Right? The whole distance from here to here is 2. We are subtracting 2 from whatever this y value is here. Okay, so we're subtracting this minus 2. And since it's still a circle, we have to square that radius. And now we have the interval from dy. Why is it minus 2 again? So just like your last function, right, this is your axis of rotation, and this is your function. So the difference between your function and the axis of rotation is your radius. And since it's horizontal, we have a y function and we have dy. Okay, now I'm going to let my calculator help me out with this one rather than doing all this. I mean, it's not hard math to do, right? I'm just squaring a binomial. So I guess we could do it. Root y times root y is y. Okay, we're going to double your central thing for root y plus for dy. Okay, so now that we've changed it into a polynomial, you can take the antiderivative using normal antiderivative rules. And when you do that, we should come out with an answer of 8 pi over 3. Okay, so when you have a horizontal rotation, right, x equals is a vertical line, which means you have a horizontal rotation. You have to have a y value integrals. You have to have y in your function, and you have to be doing it with dy, the width of your disks or width of your radiuses there. Okay, so anytime we're finding a volume that's been rotated, it's pi times an integral of the radius squared. Hopefully this helps.